what we did is refraction for spherical refracting surface, spherical refracting surface from rarer to denser. Okay, when I'm saying that diffraction is from rarer to denser, that means where is your object? Your object is in rarer medium or it is in denser medium? Yes, tell me. Yeah, object is in rarer medium. And where is the image? Image may be in denser medium. So object is in rarer medium. It's refracting from rarer to denser. Rays are coming from rarer to denser. And this was the relation n1 by minus u plus n2 by v is n2 minus n1 by r. This was the final result. N1 by minus u plus n2 by v is n2 minus n1 by r, right? This was the final result. Huh? Okay. What was N1? N1 was the refractive index of the rarer medium or it was that of the denser medium? What was N1? N1 is always the refractive index of rarer medium. And N2 was the refractive index of denser medium. See the notation in which we are deriving all these relations. In that notation, your N1 is always rarer and your N2 is always denser medium. So this is what we did in the last class. The next thing is, the next topic that we will do is refraction from denser to rarer medium. Like we will assume that your object is in denser medium and your image is in rarer medium. But before next derivation, I want you to do a basic numerical. It's given that refractive index of glass is 1.5. So if I draw the diagram is like this. This is the ray diagram basically. So this is your spherical refracting surface. This is center of curvature. This is pole of the surface. This separation is your 10 centimeter. That's your radius of curvature. This is your object. The separation between pole and object is O, which is 20 centimeter. So you know that your object distance is 20 centimeter. You just have to calculate your image distance. How much is your image distance that you need to calculate? This is air. So refractive index of the air is 1. This is glass. Refractive index of the glass is 1.5. Now solve it. Calculate image distance. So you will use this relation. See, your object is in rarer medium. Your image rays are refracting from rarer to denser medium. So you will be using this relation. But while using this relation, always remember that your N1 is that of rarer medium, N2 is that of denser medium, and you have to consider proper sign. While deriving this relation, you should consider proper sign convention. So this is the relation that we will be using. It's N1 over minus U plus N2 by V is N2 minus N1 divided by R. Now, how much is N1? N1 is of the rarer medium, which is 1. N2 is the refractive index of the denser medium, which is 1.5. U is your object distance. Remember, all distances should be measured from pole. When you and this is your object, so this should be the direction of light. This should be the positive direction. But while measuring this object distance, you are moving from pole to object. Means you are moving in a direction opposite to that of light. So that means your object distance is negative. It's minus of 20 centimeters. See how much is your radius of curvature. You're moving from pole to center of curvature. This is your radius of curvature, which is positive. It's plus 10 centimeters. It's positive plus 10 centimeters. You have to calculate V now. Let's substitute all these values here. So if I substitute this n1 is 1, u is minus 2, 1.5 minus 1 by r. So it's 1 by 20. It's zero point 0.5 divided by 10. 0.5 by 10 minus 1 by 20. So 1.5 by V is 20. It's 1 minus 1, 0. Let me check once again. Maybe 0 means your rays will become parallel. N1 is 1, N2 is 1.5, U is minus 20, R is 10, 1.5, 0.5 by 10. Radius of curvature is 10 centimeters. Yes, it would be infinity now. It should be infinity. 1.5 by V is your LCM is 20. It's zero point 0.5 multiplied by 2 minus 1. So it's 1.5 by V is 0 by 20. So you can say that your V by, I'm taking reciprocal on both the sides. So that will be 1.5 by V is equal to 0. If I take reciprocal on both the sides, it's V by 1.5 is 1 by 0, which means your V by 1.5 is infinity. Your V comes out to be infinite, means your final image will be at infinity. V infinity means after refraction, rays become parallel to principal axis. So if I draw the ray diagram properly, I'm drawing the ray diagram on the next page. So this is your surface. This is the principal axis. This is the pole. This is center of curvature. This is your object. This is the incident ray. After refraction, the ray becomes parallel to principal axis. This distance is 20 centimeter. Infinity means ray will become parallel to principal axis after refraction, and this is the 10 centimeter distance. So this is the surface. This is N1, which is air. This is N2 glass, which is 1.5. This is the principal axis. Yes, yes, ray diagram have marks. Yes, ray diagrams have marks. This is center of curvature, and this is your object. Okay, let's see this thing now. How much is object distance? Your object is placed at a distance of 100 centimeter. So this is your 100 centimeter. This is 100 centimeter. Your object distance is minus of 100 centimeter. How much is R? Your R is, it's 20 centimeter. It's plus 20 centimeter. P2C, this is your R plus 20 centimeter. N1 is 1. N2 is 1.5. Now if I substitute all these values here, your N1 will be 1 minus of minus 100 plus N2, which is 1.5 divided by V. N2 minus N1, which is 1.5 minus 1 divided by R, which is 20. So I'm left with 1 by 100. It's 0.5 divided by 20. So you can write that 1.5 by V is 0.5 divided by 20 minus 1 by 100. So you can write that 1.5 by V is the LCM is 20. See, the LCM is 20. It's 0.5 into 5, right? No, not LCM is not 20. LCM is 100. 25 is 100. So it's zero point 0.5 into 5. Minus, it's 1. So we are left with 1.5 by V is, it's zero point 0.5 into 5, it's 2.5 minus 1. It's 1.5 by 100. 1.5 will cancel this 1.5. V is 100 centimeter. The next derivation is from denser to rarer medium. Means if your object is in denser medium and your image is in rarer medium. The next is for refraction from denser to rarer medium. So next is from denser to rarer. Means your object is placed in denser medium and your image is in rarer medium. Denser to rarer for convex refracting surface. See, instead of convex, if you are taking concave surface, then again your answer will remain same. The equation just depends whether refraction is from rarer to denser or refraction is from denser to rarer. That's it. It does not depend on the shape of your surface, whether your surface is concave surface or convex surface. Even if your surface is convex or concave, the relation will be same. The relation just depends upon rarer to denser or denser to rarer. So let's start this calculation. So this is your spherical surface, a convex refracting surface. See, in all calculations, whenever I write N1, N1 is my rarer medium. Whenever I write N2, that means it's denser medium. So if I'm writing from denser to rarer, where should be my object? My object should be in rarer medium or my object should be in denser medium? Tell me. Your object is in denser medium. This is your object. This is your object. This is the center of curvature of the system. So this is it. This is my incident ray. I need normal on the surface just to decide whether the ray will refract from rarer to denser or denser to rarer. I need normal. How to draw normal on a spherical surface? No. Normal is the line connecting the point to the center of curvature. If you remember your class 9 geometry, if I ask you to draw a normal on the sphere, what you do is you connect that point to the center of the sphere. Means all radius are normal to the sphere. That's it. Similarly here, it's a spherical surface. If I'm asking you to drop a normal on the sphere, then just connect this point to the center of curvature. This is normal. This is 90-degree angle. So this is your normal. This is your angle of incidence. Okay, just tell me, your ray is moving from denser to rarer. This is the denser medium and this is the rarer medium. So how it will bend? It will bend towards the normal or it will bend away from the normal? It's moving from denser to rarer. How this ray will bend? Very good. It will bend away from the normal. So how you decide whether it's towards or away? It's like if there was no refraction, then this ray would have traveled in this direction. If there is no refraction, then ray would have traveled in this direction. But due to refraction, your ray will bend away from the normal. It will go here. Your ray will bend away from the normal and it will go here. This is your refracted ray. And see, this is your normal, this is refracted ray, this is known as angle of refraction. This is angle of refraction. The next is, we call this angle as alpha. I call this as gamma. And this is my image, right? There is one ray which is going like this, another ray is passing through the principal axis. This will ray go straight, these two rays will meet over this point, and this is your final image. And we call this angle as beta. The next task is to this, I call this as M, and this is I, and this is C. In triangle, I'm taking triangle OMC. Can you tell me which one is the exterior angle? Good. Gamma is the exterior angle, right? So alpha plus I is equal to gamma. You can say that your I is gamma minus alpha. That's my first equation. That's my first equation. That's your I. Gamma minus alpha, that's my first equation. Similarly, I need another relation, that is CM and I. In this triangle CM and I, which one is the exterior angle? Exterior angle is the angle which is between the extended side. This is the extended side and this is the side. This angle would be the exterior, not this one. It's not the extended side of the triangle, this one. It's always between the extended side. So this side is extended and this is it, this is R. So in triangle CMI, I can write that gamma plus beta is equal to R. Let's call this as equation number 2. This is R, which is gamma plus beta. So now we have I and R in terms of gamma, alpha, beta, and gamma. Next, what we can do is we can simply apply Snell's law. When I apply Snell's law, it's N2 and the angle here is I. So I'm writing it as N2 sin I. See, each and every step is similar now. The only difference is in the value of I and R. If you look at the last derivation from rarer to denser, each and every step is same now. N2 sin I is N1 sin R. If I apply small angle approximation, I am using small angle approximation. Then sin I is almost equal to I and sin R is approximately equal to R now. Sin I is equal to I and sin R is equal to R. So instead of sin I can write I. Instead of sin R, I can write R. So it's N2I, which is equal to N1R. That is my third equation. Now what you can do is just simply substitute the values of I1, I and R from 1 and 2 and 3. Just substitute equation number 1 and equation number 2 and 3. When you do all these substitutions, it's N2I, which is gamma minus alpha. R, which is gamma plus beta. This is it. So I call this as my equation number 4. The next task is to somehow convert this alpha, beta, and gamma in terms of sides, in terms of length. So for that, we can do this thing, like we can drop a normal here. Let's drop a normal here. To calculate these values of alpha, beta, and gamma, just drop a normal here. So I call this as n. So now we can calculate alpha from triangle OMN. To calculate alpha, I can use triangle OMN. In triangle OMN. Okay, tell me how much is tan alpha in this triangle? Mn by NO. It's perpendicular upon base. Mn by NO. Or you can use small angle approximation. You can write that tan alpha is approximately equal to alpha, which is equal to Mn divided by NO. I call this as equation number 5. Next, what we can do is we can calculate beta. in triangle. For beta, we can use MNI. MNI. Stan beta is approximately equal to beta, which is equal to perpendicular upon base, Mn by Ni. It's Mn divided by Ni. This is equation number 6. Similarly, I can take this MNC in triangle MNC. Fatma, how much is tan gamma? Just tell me quickly. Yes. It's Mn by Nc. Mn by Nc, right? It's tan gamma is, okay, I'm writing it. Tan gamma is gamma, which is Mn divided by Nc. That is equation number 7. So now I have the value of alpha, I have the value of beta, I have the value of gamma. What I can do is I can substitute all these values of alpha, beta and gamma that we have calculated in 5th, 6th and 7th in equation number 4. Now let's substitute 5, 6 and 7 in 4th. 5, 6, 7 in 4. We will substitute all these values in 4. So it's N2 gamma minus alpha. It's Mn by Nc minus alpha. How much is alpha? It's Mn by No is equal to N1. Gamma plus beta. Gamma is Mn by Nc plus beta, which is Mn by Ni. Now this Mn will keep on cancelling this Mn. This Mn will get cancelled out. And we are left with N2 by Nc minus N2 by No, which is equal to N1 by Nc plus N1 over Ni. That is equation number 8. Now see, this N and this P are very close. This surface have a very small aperture. So this N and P, these 2 points are very close. So this is your object distance U. So you can say that NO is almost equal to PO, which is basically your object distance. Tell me, your PO is positive or negative? Just check the sign convention. Aperture is small. Check the sign convention. Aperture is small, so N and P are very close. These 2 points are very close. So you can say that NC is almost equal to PC, which is equal to positive or negative sign. NC is PC. And how much is PC? PC, how much is PC now? That's minus U. Similarly, do one more thing. Tell me the sign convention. How much is PC? What is PC? P to C separation? You don't know. See, C and P radius of curvature. Center and pole, this is the radius of curvature. So you can write this as NO basically. Just a second. This is NO, this is PO. Huh? This is NC, which is almost equal to PC. This is R. Tell me the sign convention. It's plus R or minus R? Yes, it should be negative minus R. Very good. So both are correct now. Minus R. There's one more distance. What is the name of this distance? PI, pole to image. Yes, it's V. Image distance V. So NP, NI or PI are same thing. Huh? Ni is almost equal to Pi, which is equal to V. These are equation number 9. Next, what you can do is you can just substitute 9 in 8. It's N2 by NC minus N2 by NO, N2 by NO, which is minus U. It's N1 by NC, which is minus R, plus N1 by Ni, which is V. N1 by minus R plus N1 by V. Now what we can do is just take this N1 into the left hand side and take this term to the right hand side. So I'm left with N2 by U minus N1 by V is N1 by minus R plus N2 by R. I just shift this term to the right hand side so it becomes positive. I shift this term to the left hand side, it becomes negative. So now what I have is just to bring this thing in a form that was in the case one, like for rarer denser, just to match it with the previous form. Okay, let's write. It's N2 by U minus N1 by V N1 by minus R plus N2 by R. So this is the expression, but just to convert this in a form that match with the case of rarer to denser, I'm just multiplying the whole term with a negative sign and also this with a negative sign. This I can do, right? I can multiply both the sides of the equation with a minus 1. I'm doing this just to bring it to a standard form that you can remember easily. So if I multiply with the negative sign, then it will be N2 by minus U plus N1 by V is N1 by R minus N2 by R. Or you can say this is N2 by minus U plus N1 by V is N1 minus N2 divided by R. This is for refraction from denser to rarer. And one more thing, whenever you want to use this relation in a numerical, you have to use proper sign. Always consider proper sign. Always consider proper sign when using this relation. So you have N2 by minus U plus N1 by V is N1 minus N2 by R. So if you compare this relation with this one for rarer to denser, see the same expression. Just instead of N1 you have N2 and instead of N2 here you have N1. So if you can remember the formula for rarer to denser, for denser to rarer, what you will do, just convert, replace 2 by 1. That's it. In this expression, if you replace 2 by 1 and 1 by 2, then you will come back to the same equation. You will come back to the same equation, this equation, denser to rarer. So no need to memorize both the relation, just memorize one of them and another one will follow. Combination of two spherical surfaces. So lens is just the combination of two spherical surfaces. So if you combine two surfaces, then you get a lens. Those two surfaces could be, say, you could have two convex surfaces, two concave surfaces, one convex, one concave, one convex, one plane. So if you have two convex surfaces, say, let's you have two convex surfaces. If you have two convex surfaces, both the surfaces are convex, we call this as biconvex or double convex lens. You can call it biconvex or you can call it double convex lens. Next, what you can do is you take one plane surface and then a convex surface. We call this as plano-convex lens. One plane and one convex surface. We call this as plano-convex lens. Next, what you can do is you can take one concave surface and another convex surface. One concave and one convex surface. We call this as concavo-convex. Then there is concavo-convex lens. Next, what we can do is we can take two concave surfaces. Both the surfaces are concave. I can take both the surfaces as concave. Two concave surfaces. So this is either biconcave, or it's double concave. Or what we can do is we can take one plane surface and another concave surface. If I take one plane and one concave surface, I call this as plano-concave. I call this as a plano-concave lens. You can do one more thing. You take one convex surface, one concave surface. We call this as convexo-concave lens. So these are the two types of lenses that you should, six types of lenses basically. Three types of convex lenses, three types of concave lenses. The next thing is the optical center of the lens. The next is the optical center of the lens. Optical center of the lens. So optical center means the center of the lens. The rays passing through this optical center will not deviate. Like if I take a thin lens, this is a thin lens. So whatever we study, whatever we will derive everything for a thin lens. Though I'm not drawing a thin lens, but this is a thin lens. No, very, very thin lens. This lens is so thin that the separation between P1 and P2 is negligible. It's a very thin lens. And this is the optical center of the lens. This is what we call the optical center of the lens. So if you can pass a ray which is passing through the optical center of the lens, then this ray will pass without any deflection. This ray will pass without any deflection. The ray passing through the optical center will not deviate. It will go straight without any type of deviation. This is what we mean by the optical center of the lens. Even if you have a concave lens, even if you have a concave lens, this is your concave lens. This is the optical center. The ray passing through the optical center will not undergo any deviation. It will go without any deviation. This is mean by optical center of the lens. So rays passing through optical center will not deviate. It will go straight. After this optical center of the lens, the next thing is focus. Focus of the lens. So focus simply means if you have a lens, this is the lens. So these are the rays parallel to the lens. The rays parallel to the lens converge at a point, and this point is known as focus. Just 1 second. So rays coming parallel to the principal axis converge at a point. This point is known as second focus. So second focus, or its full name is second principal focus. Second principal focus of the lens. The point at which parallel rays converge is second principal focus. See, this is the optical center. The separation between the optical center and the second principal focus is known as second focal length. This is known as second focal length of the lens. This is the second focal length of the lens. Second principal focal length of the lens. Just like second principal focus, we also have first principal focus. See, what do you mean by first principal focus? I take this convex lens and I placed object at a point O. This point is like after refraction through the lens, rays become parallel to principal axis. This point is known as the first principal focus. This is F1. This is F2. So this is what we call first principal focus. This is the first principal focus. So first principal focus is that point on which if you place the object, then rays become parallel to principal axis after refraction. This is known as first principal focus. And this separation is known as first focal length. First focal length. But when I say focal length of a lens, then by default, focal length of a lens means the second principal focal length. Remember always, by default, focus of lens means second focus. Although there are two focus in the lens, but we always use second focus in derivation, in calculation everywhere. By using sign convention, can you tell me this F2 is positive or negative? Just tell me, is it positive F2 or this is negative? Very good. Second principal focus is positive. No, Fatma, it's positive. See? Okay. In lens, we measure all distances from the optical center. All distances from the optical center. So you're moving from optical center to focus. You're moving in the direction of light. That's why it's positive. So I'm writing it here. In lens, we measure all distances from optical center. We measure all distances from optical center. So that is the focus. We measure all distances from the optical center. So if you're moving in the direction of light, then your focal length is positive. If you're moving in a direction opposite to that of light, here, just like here. See, this is optical center. You start from the optical center and move up to F1. Start from the optical center and move up to F1. You're moving in a direction opposite to that of the light. So this term is negative. But whenever we talk about the focus of a lens, we always talk about the second focus. We always say second principal focal length of a lens, and the second principal focal length of a lens is a strictly positive quantity. After focus, next thing is my focal length of concave lens. Instead of convex, if I take a concave lens, if I take a concave lens, then in concave lens, the second principal focus means if you take rays parallel to principal axis, then remember concave lens will not converge these rays. It will simply diverge these rays. The rays gets diverged. The rays gets diverged. So when you meet these rays in the opposite direction, if you so the concave lens does not converge, it's basically diverge the rays. But when you produce these rays in the backward direction, when you produce these rays in the backward direction, they appear to meet at a point, they appear to meet at a point here. This point is known as second principal focus. And this distance is the focal length. Can you tell me whether this is positive or negative? This is the optical center. Is it positive or negative for a concave lens? Good, Jumena. Fatma, Afroza, is it positive or negative now? You're not moving in the direction of light, right? O to F2, you are moving in a direction opposite to that of light. So your F2 is negative term. It's negative. We can do one more thing. Like what we can also do, we can define first principle focus. First principle focus. So here, first principle focus means it's a point over which if I converge my rays, if I converge my rays over the first principal focus, then after refraction, these rays will become parallel to principal axis. If I converge my rays at first principal focus, then after refraction, these rays will become parallel to principal axis. We call this point as first principal focus. The rays becomes parallel to principal axis. The point at which rays appears to converge, and after refraction, they become parallel to principal axis. That's first principal focus. This is the optical center. So if you can check, say O to F1, you're moving in the direction of light. That means your F1 is not negative now, it's positive. The next is Lensmaker formula. Another 5 marker question from this chapter. Lens maker formula. So Lensmaker formula is just a relation between object distance, image distance, or instead of object distance and image distance, you can even take focal length. The relation between focal length of lens, focal length of lens, object distance, and image distance. Not sorry, object distance. Radius of curvature and refractive indexes. So Lensmaker formula is the relation between these quantities: focal length of lens, radii of curvature, and refractive indices. So I'm deriving this Lensmaker formula for a convex lens. For concave lens, the steps will be exactly same. No change in steps for the concave lens. So this is your convex lens, double convex lens. This is the optical center of the lens. See, this is N1, surrounding refractive index. This is N2, the refractive index of the medium of lens, and this is N1 again, the refractive index of the surrounding. On both the sides of the lens, medium is same. Both the sides is the surrounding is N1 only. See, there are two surfaces. This is one convex surface. This is another convex surface. You have two refractions. This is the pole of the first surface. This is the pole of the second surface. But the lens is thin, so I will use an approximation here. Like if I measure distance from P1, or I measure distance from O, or I measure from distance from P2, that's the same thing. I'm using thin lens approximation here. In the complete derivation, I will use this simple thin lens approximation. This approximation says P1, O, P2 are close, very close points. So whether I take separation from P1 or I take separation from O or I take separation for P2, they're the same thing. You will get the same result. So this is my object. I call object as O1. This is my object. So I'm considering my first refraction from this surface. Can you tell me the shape of the surface? It's a convex or a concave surface? Towards the rarer medium, you have this convex side. It's a convex surface. This is P1, so the center of curvature of the first surface is here. The center of curvature of the second surface is here. This is C2. Next is, let's draw a normal over this point. So to draw a normal over the surface, we know that we have to connect that point to the center of curvature. So to draw normal, we connect the point to the center of curvature. We have connected the point to the center of curvature. This is the normal. I should use a different color for normal. Let's say this is the normal. This is the normal. Now see, rays are moving from rarer to denser medium. Rays are traveling from rarer to denser medium. If there would be no refraction, then ray would have traveled in the straight line direction like this. But since it's moving from rarer to denser, so it will bend. It will bend towards the normal. But if you look at carefully, see, when ray reach here, it's moving from denser to rarer. It will again undergo refraction. You're getting me? When the rays are moving from the lens to the surrounding, it's again moving from denser to rarer. If it is moving from denser to rarer, it will again refract. So see, this should be the direction of ray if there is no second refraction. I call this as I1, image I1. It's an intermediate image. I'm explaining it again. This is X, this is Y, this is my object. I incident this ray over the first surface, which is xp1y. Ray is traveling from rarer to denser. If there was no refraction, then ray would have traveled in this direction. But since medium is changing, so ray will refract. It's moving from rarer to denser, so it bent towards the normal this way. But now again, when the ray is moving from lens to the surrounding, there should be one more refraction. If I don't consider that second refraction, then ray will go straight and it should have met here. This I1, I call this I1 as my intermediate image. Intermediate image. So for the first surface, xp1y, this is your object. This is your object distance u. This is your object distance u for the first surface. This is the object distance u for the first surface. See, I should take object distance from P1 from pole, but I had just have mentioned that Flynn lens approximation P1, O and P2 are very close. So whether I take it from O or take it from P1, that's the same thing. Similarly, what I can do is I can mark this distance of optical center to the image. Let's mark this distance as V1. Similarly, you can mark this distance, this O to C1. We call this distance as R1. This is the radius of curvature R1. This is for the first surface xp1y. But what happened is when the ray moved from the lens to the surrounding, there should be a one more refraction. There should be one more refraction because it's moving from glass to air. So let's again draw another normal on the surface. This is the another normal. This is the another normal, second normal. This is again normal. But now your ray is moving from glass to air, it's moving from denser to rarer medium. So it will not bend towards the normal. It will rather bend away from the normal. It will bend away from the normal, like it will bend here. This will be your final image. This is what you see through a lens. This is your object for the surface. This is your image for the first surface. For the second surface, this I1 is the object. For the second surface, this I is the image. So I'm using another color to mark these distances. This distance is R2 and this distance is V. This is R2 and this is V. I'm repeating again, although I should have taken this R2 distance from the pole, but it's a thin lens, P1, O, P2, all are very close. So whether I take it from O or I take it from P2, that's the same thing. So I'm taking all distances from O. Just make this ray diagram. These two are normal. This red color and this blue color line are normal. Okay, the next is, okay, now let's start derivation. I'm considering first the surface xp1y. For the surface xp1y, refraction is from rarer to denser. Refraction from rarer to denser. U1 is object and I1 is image. See this O1, this O1 here, this O1 here. This is the object and this I1 is the image. So for rarer to denser, you know the formula is N1 by minus U plus N2 by V. Instead of V, I will take V1. See, I have represented this separation as V1. Is N2 minus N1 divided by R1. That's my first equation. If I consider another surface, surface XP2Y, if I consider another surface which is XP2Y, for the surface XP2Y, this second surface, if you look at carefully, your ray is moving from glass to air. Means your refraction is from denser to rarer medium, not from rarer to denser, it's from denser to rarer medium. Refraction is from denser to rarer. You can write this as it's N1, not N1. If I and what is object? I1 is object here. I1 is object here. The image of the first surface is the object here. And I is the image. I mean this distance is the image distance V1. This V1 is the object for the second surface. This I is the image for the second surface. For the second, for denser to rarer, we know that the relation is N2 by minus U. But instead of U, I will use V1. Because for the second surface, I1 is the object. And this is the object distance from O to I1, that's V1. N2 by minus V1 plus N1 by U. N1 by V, which is N1 minus N2 divided by R2. That's second equation. Next, what we can do is just add 1 and 2. Just add these two equations, 1 and 2. When I add these two equations, that means I add N1 by minus U plus N2 by V1 plus N2 by minus V1 plus N1 by V is equal to it's N2 minus N1 divided by R1 plus it's N1 minus N2 divided by R2. This is it. So this N2 by V1 will cancel this N2 by V1. I can take this N1 as common. If I take N1 as common, I'm left with 1 by V minus 1 by U is, and you can take N2 minus N1 as common here. This is N2 minus N1. It's 1 by R1 minus, see, I'm just taking the negative sign common here. So it would be N2 minus N1. I'll be left with 1 by R1 minus 1 by R2. And if you can remember Lensmaker formula, you can say 1 by V minus 1 by U, lens formula. 1 by V minus 1 by U is 1 by F. Instead of this 1 by V minus 1 by U, I'm using 1 by F. So this is N1 into 1 by F is equal to N2 minus N1 multiplied by 1 by R1 minus 1 by R2. Now you can divide right hand side with this N1. So I'm left with 1 by F is N2 minus N1 divided by N1 into 1 by R1 minus 1 by R2. So I can further write this as 1 by F is it's N2 by N1 minus N1 over N1 1 by R1 minus 1 by R2. N1 will cancel this N1, it's 1. So 1 by F is it's N21 minus 1 1 by R1 minus 1 by R2. This is 1 by f, n21 minus 1, 1 by r1 minus 1 by r2. So see here, what is n21? It's refractive index of medium of lens with surrounding. Here f is the second principal focus of the lens. Second principal focal length of lens. R2 a radius of curvature. And remember one more thing. While using this formula in numericals, you have to consider proper sign. To use this formula in numericals, always consider proper sign here. Okay, so that was about lens maker formula. The derivation is same for concave lens. Step by step, each and every step is same for concave lens. Just a small difference in ray diagram. So I'm writing same steps, not just steps, same calculations for concave lens. There is no change in calculations. Okay, so just to show you how this formula works, I'm taking an example. I'm taking this simple, very simple lens, a double convex lens. N1 for the double convex lens is 1. N2 is 1.5, and this is surrounding again, N1 is 1. The radius of curvature for the first surface is 10 centimeter. This much, which is C1. And this is your second surface. This radius of curvature R2 is 20 centimeter. We should take all separations from here. It's 10 centimeter. Now you're supposed to calculate the focal length. So for focal length, you will use this relation. 1 by f is n2 by n1 minus 1, 1 by r1 minus 1 by r2. So light is coming in this direction. So when I move from optical center to C1, my R1 is positive. R1 is plus 10 centimeter. I'm sorry. To measure this R2, I'm moving from optical center to C2. I'm moving in a direction opposite to that of light. So your R2 is minus 20 centimeter. N1 is 1. N2 is 1.5. If I substitute all values here, I will get 1 by f is N2, which is 1.5 by 1 minus 1. 1 by R1, which is 1 by 10, minus of minus 1 by 20. So your 1 by f is simply, it's 0.5. LCM is 20, I think, huh? So 2 plus 1, 3 by 200. So your 1 by f is 0.5 into 3. 1.5 by 200. So your f is not 200, sorry, it's 20. It's 20. It's 20. 20 by 1.5 of centimeter. So this is how we use Lensmaker formula in numericals.